if-else. This is the, again, flow control operator. We did have flow control previously, which I think was there was an if operator and a then operator. Or what was it? The two merge, if and merge. The two separate, you see the merge operator still there. Those were two separate operators that were very, very difficult to understand. I avoided using them under all circumstances because I just never could get it right to do the if and then merge the things back together based on that if selection. There are a few examples out there of doing if merge operation pairs. I think some of the models that are published that look at do you want to stretch to 8-bit output? That's a common example using if merge, and that's actually one of the things that I'm doing here. That the if-else combines that what used to be two separate, kind of difficult to understand and put into your model operators into one model that basically says if this condition is true. So my first port is my test. You see it down here in the properties dialog, lower right. If my test is true, then pull data down this leg, this port. This is the if true port. So if the condition is true, execute everything upstream of this branch. If this condition is false, then execute this branch of the model and everything that's required upstream of that branch to feed information through that particular port and through this particular operator. So it becomes very, very easy, or certainly I think it becomes very, very easy to understand what's happening. I'm basically saying I either want to execute this bit of the model or I want to execute this bit of the model depending on some other condition, which could come from something else executing within the model elsewhere, or it could, like in this case, it's just a prompt to the user, which is, do you want to stretch to integer? So this model, we'll talk about that in a minute, basically produces something that is generally, can either be floating point output or I can stretch it through a statistical operation, say a min-max stretch of the data, and produce something that could be the same data range as my input multispectral imagery, and I could output it as integer values. So I have a flag. Do you want to stretch to integer? If that flag is true, yes, I do want to stretch to integer. It's going to do this bit of the model, which basically does this little subset here, which is look at the statistics of my input, get the minimum, get the maximum, and then do a stretch across that data range, and then just output it as an integer. If I don't want to stretch to integer, it'll execute this, which basically just takes my original data pre-stretch and feeds that into a float 32 data set instead. So I have two raster outputs in my model, but depending on how this flag is set, I'll only ever get one of them. I'll either get my integer output or I'll get my float output. And I could have done that different ways. I could have actually set this data type flag and just used one operator, but I built it this way. What does the rest of the model do? Because there's some new operators here as well. One of the things we get continuously asked for is with principal components. Principal components is a very useful technique. It's been around for a very long time in remote sensing to help take multispectral data and reduce it to a smaller number of principal component bands that contain the majority of the variability from the input image. So if I have a 7-band input image, it may well be that, if I look at the principal components, the first 3 principal components encompass 99.9% of the variability from the original data, so I can throw away the other n principal components and just keep the first 3. And we have, pre-canned principal components functions in Imagine, but what they don't do is tell you what contribution each principal component makes to the original variability of the data. So it's actually very easy to get that information. You just need the eigenvalues, and sometimes the eigenmatrix, but it's mainly the eigenvalues that you need from the input multispectral data. And from those eigenvalues, the eigenmatrix is what you use to calculate the principal components, but the eigenvalues that are present in that eigenmatrix are what you can use to determine the amount of variability that was inherent in each of those principal components. So there's a little bit of complexity going on here. We look at the input. Where is it? There's my raster input. I need to set zeros to no data so they don't influence the principal component calculation. I then take that raster information, I look at how many bands it has and how many numbers of principal components I want to produce, and I do some magic over here that basically alters the eigenmatrix. So if this is a 7-band image, normally you'd have a 7x7 eigenmatrix, but if I only want 3 principal components, I need to modify that eigenmatrix so it's only 7x3 to multiply through to only get 3 output principal components. I need to then look at the size of this matrix and trim it by the inverse of the number that I want, and so on, until I get that particular matrix subset. And then just a linear combination does that multiplication of, say, a 7x3 matrix with my original data to get the actual principal component values. But what I do down here is I also pull out those eigenvalues, look at the GIS statistics, and then I basically sum those statistics for each of the eigenvalues and divide by that sum. So each one gets divided by the sum, multiplied by 100. So that gives me a statistical output, and the report is one of the new operators. Might actually have been in 2015, 15.1. But what this now does then, if I click run and give it an input multispectral data set, perhaps the same iconos image, say how many principal components I want, or the name of the output image file, number of principal components, let's do all 4, skip factor on the statistics. One of the important things here is my 2 output reports. I can do one on the eigenmatrix. I can do matrix out. I can do value, or let's call it contribution out. And there's that flag on the if-else operator. Do I want to stretch it to an integer or leave it as float? So let's go ahead and run that, and that'll run. And whilst I talk about that, you'll notice I said stretch to integer. I didn't say stretch to 8-bit or stretch to 16-bit or anything like that. I said stretch to integer. And the reason I said that is that I don't stretch to a fixed integer data range. I use another new operator from 2016, which is the get actual bits per pixel operator. That's that guy up here, sat up here, taking in various bits of information, including my raster input data. Actually, it's taking the data in after having set the no data value to 0. And it's also taking some information in from the statistics, so it knows the statistical range. Because what this does is it looks at the input data, and that iconos image was stored as a 16-bit integer. But actually, iconos only has a true 11-bit data range. It goes 0 to 2047. And probably actually not even 0 to 2047. It's probably something like 6 to 2018. Whatever it may actually happen to be. So I could in the past have just looked at the raster input and said, oh, the raster input is 16-bit, so I want to stretch my output data across the 16-bit data range, the whole 16-bit, and output a 16-bit integer. I don't want to do that here, though. I want to try to retain the integrity of my original data. So I actually look at the actual bits per pixel, and you can see here, because I've run the model, it actually has a value filled in. It looked at the input data set, and based on the each input band, it looked at the statistical range and said, really, that's only 11-bit data. Its actual bits per pixel is an 11-bit data range. I then take that number, 11, and do a power function. I do 2 to the power 11 to get the maximum data value I might have had based on that data range, 2048. Really, I probably should have subtracted 1, but hey-ho, never mind. And then when I do the stretch, you remember I come in here and I do my min-max, I'll get my min and max values. I use that to stretch the data across a range that is multiplied up by 2048, so that rather than 0 to 1, it's 0 to 2048, and then I trim that to an 8-put 16-bit integer. So I've retained the integrity of my input data, my principal components effectively are still 11-bit, and so on. But just to show you, that's one potential use of the get actual bits per pixel. If you're doing stretching of data, processed data, and you want it to match kind of the range of the original data, you don't want to just go off the input data type of 16-bit, or even potentially you don't want to go off the max statistical value. You want to spread it across the general range that the data might have been, and the get actual bits per pixel is a very useful operator for doing that. Excuse me. Okay, that's that one.